While Stuart's getting the first slide together, I want to just tell you that most of you know that we've been working on this telescope, and I just want to say that when two old guys like Stuart and I get together to make a telescope, you can be sure of three things. That number one, you're going to generate a lot of sawdust and wood chips. Number two, a lot of metal chips. And three, a lot of methane.
Expand upon
it. We expanded a lot.
You're saying it's all like Titan.
So tell us, how did this project influence your marriage?
Well, you know, while we're waiting on this, let me just acknowledge my wife, Pam, who's here. She's been very, very patient and a really good sport, because for the last 2 years I've been slogging up the hill to Stuart's house a couple of days a week and staying well into the night. And she's been extremely supportive and good-natured about it, and thank you, Pam. Aha!
Before I ever started this, so
there we go. All right.
that's why I can do it.
Okay.
All right.
Well, without further ado, just about all of us that are familiar with astronomy and telescopes know that when it comes to telescopes, aperture is king. Size matters. The bigger the telescope, the more light it can gather, and as a consequence, fainter objects become closer, and more closer objects become more brilliant and bright and more detailed and more magnificent to behold. Now, I don't want you to get the idea that I'm demeaning smaller aperture telescopes, not in the slightest. I own several smaller scopes and use them regularly. However, given the opportunity to have big aperture, that's what I would like to have. Unfortunately, larger aperture telescopes are beyond the reach of most amateur astronomers due to several reasons. Cost being one of them, relative complexity, heavy weight, lack of portability. All of these things keep bigger scopes out of the hands of most of us. And if you're like me and have gone to star parties and had a chance to look at some of these really nice big Dobsonians, 15 inches, 18 inches, 20 inches, and so forth, it doesn't take much for you to get a serious case of aperture fever, which I have, admittedly so, and proud to say, and will probably have as long as I'm in the hobby. But as we said, unfortunately, big scopes like this are out of the reach of most of us. But what if? What if a relatively simple to use, large aperture, high quality telescope could be made available as a club instrument, as a club telescope, available to anybody in the club that's interested and willing to take a little bit of training and orientation? Well, this is the dream that Stuart and I have been pursuing for about the last 4 years. Actually, Stuart has been thinking about this even longer than that. But about 4 years ago, he and I sat down to talk about such a telescope, and we agreed that to have this kind of an instrument available to the club would be a really great thing. So what we're going to talk about tonight is everything that's ensued since that first meeting that Stuart and I had, the design and the conceptualization, the actual work that's gone into it, and the ultimate realization of the instrument. Now I want to give you just a little bit of background. The optics for the telescope that we're going to talk about tonight, the DAS444, we believe are good. They originally were in an old, outdated telescope that was owned by the club that didn't get used much and resided in Chamberlain Observatory. And it sat there until the observatory was remodeled, and Dr. Bob took over the office where the scope had been. So the scope became an orphan, and Stuart took the orphan home. And after evaluating it, he but carefully, he realized what he already knew, that the chassis that the optics in were junk. It had an inferior mirror cell, inferior secondary support. It was heavy. Basically, what you had was Rolls-Royce optics in a Model T chassis. So Stuart trashed all the chassis and kept the optics, but all the while he had the plan that one day the primary mirror would be put in a telescope that was really worthy of the optical, the primary mirror and the secondary itself. So we sat down, as I said, about 4 years ago, decided this kind of a telescope would be a great thing to do for the club, and reviewed some PLOP software, which was used in designing the mirror cell. And we decided, yes, we're going to do this. We're going to build this. I think Stuart had the idea for a long time, but I was able to convince him that I had the zeal and the enthusiasm and the commitment to really do this. We did have a little bit of a gestation period, but about 2 years ago, as a matter of fact, 2 years in August, we actually bought the wood and sat down and began to do the actual construction. Now, as I said, we have envisioned this as a club telescope. And one of the things that's nice about it is that it's portable. Ultimately, we hope to find a home for it at the dark site. But until that time, we have the ability to store it, take it to the dark site, take it to star parties, and so forth. We would expect that it's going to have to pass some litmus tests. But we do, as I said, hope to have it, a home for it at the dark site. And I would hope to be the manager, caretaker of the instrument and develop a nucleus of people that would share the responsibility with me for the care and the feeding and the upbeating and the training and so forth. And I want to assure Daryl that we want to do this in a way that isn't going to make any more work for you. Now, I want to talk about Stuart a little bit since we don't have a bio. Those didn't get here. Stuart's been a big player in this club. He's been a big player in this club probably since the early 2000s, about twice as long as I have. He's been past vice president, board member. He's been a public night speaker. He has taught a class in mirror making. And he's just generally been a great volunteer, one of the most helpful, generous people that I've met in the entire group. And as I said, Stuart's been dreaming and scheming about this project even longer than I have. I also want to say that the design of this instrument and all the heavy lifting in terms of the woodworking, the machining, the metalworking, the real heavy lifting is all done by Stuart. I've been the enthusiastic, helpful apprentice, support system, gopher, vacuum runner, whatever was needed and wanted. Whatever was needed and wanted to get this going. So at this point, I'm going to turn this over to my partner in crime, Stuart Hutchins.
Well, it's been a while since I've been in this hall. I see a number of familiar faces up there, and will this pick up on my pocket like this? Can we hear? Okay. See a number of familiar faces up there, and some that I haven't seen before. Anyway, it's good to see you all, and it's good to be here again. I'm one of those rare people. My whole life is designing and building things. I like to design, I like to work with my hands, I like to do things, and I think I found the perfect hobby because if the sky is light, the clouds are heavy or whatever, you can build telescopes. And on those rare occasions when it gets dark, then you can go and you can look through the telescopes. So I keep busy. This is a couple of pictures. This one here we showed before. We made a presentation, a premature presentation sometime last year, I've forgotten when. This is what we have here today, plus those. So we have an almost complete OTA, optical tube assembly. This has been the most difficult part, both design-wise and construction-wise. I have a little cheapy milling machine which I inherited from my son. No, he's not dead, but he got a PhD in computer science. He works for Google now, and so he doesn't need his milling machine. I also have a lathe. I also have woodworking tools. I also have things to start fires with. I mean, whatever you need, I got it. So, like I say, I like to build things. Problem with building things is it takes a long time, takes a lot of thought to design, et cetera, and so forth. So, we have something in similar, or in common with NASA. Granted, our staff is less numerous, our budget is much smaller, but we're having trouble with the integration phase of this project, and so it's taking a little bit long. It's just like the James Webb otherwise. So, these are the parts we have here, and I'm going to show you I'm going to show you right now how it goes together. Hang on to that.
What's the heaviest part?
It's going to be the mirror in the mirror box. About 60 pounds.
Really, I don't know. All right. I'm going to go that way.
If I swing this way.
In theory, these are interchangeable, but we have them marked just in case.
I'm not going to get in this because we want you to see it. This is a one-hand job. It's 4.5, 2,000 millimeter 4.5. You're going to see that Kirby. As a matter of fact, I think our one of the many elegant pieces in this book,
And hard to make.
and hard to make.
How many spare bolts do you keep in case you burn them in the ground?
Well, that's a good question. We're going to have a toolkit with spares in it and a manual. Although, as I said, I want to stress the guy, this is going to be a simple telescope to use. It will have a computer, but you don't have to use the computer. You just use thumb machine. Yes.
Are you going to go to captured screws with, instead of the Allen wrench, go to thumb screws? No?
So,
Is the mirror covered right now?
It is.
okay, what now?
Is the mirror covered with a suitable cover so when you drop a bolt,
Well, A, I don't drop bolts, but the cover is one of the final details that we haven't made yet. It will have a cover to protect the mirror. So this thing, I think of this as the north end. Of course, the Dobsonian is an Altaz telescope, so it rotates like this. This is an OTA. It's a Newtonian telescope. It will be placed on a Dobsonian mount. Everybody here knows what I'm talking about, right? So I don't have to get into that. So in use, this thing will be tipping that way. As it is now, you can do two things with it. You can use a stick to hold it, say in this position, or maybe that position, and look at Polaris. Or you can do it like this, and you can do as, what's his name from the 1700s did, and just watch things go by and write them down or call down to your assistant on the ground. And you too may discover 5,000 objects. So this is what it is. Square tubing. As you saw, instead of having 8 individual tubes, I have only 4 triangles. And the part down here that holds the triangles are such that you can slip them in, give those just a little tweak or maybe none, and they stand up well enough to put the cage on. You only have to tighten 8 bolts total. Everything is predetermined. Everything is the same length. It fits. That was one of the design goals. So let me move down. Digby told you some of the history of this thing. The boy speaks with a glib tongue, I have to say. This optical set is a suspected good optical set. His story of the storage of the scope in Chamberlain, the fact that we had to... Do you have a...
I know some history on that. It belonged to James Odin, and he wanted to get rid of it because he was going to travel the nation in his pop-up trailer and go places, and that old Coulter had was too big for his travel, so he just gave it to us. We checked out the mirror. It was about halfway over, so we had Jerry Robertson refigure it.
Okay.
And it just sat there after that.
That's part of the history that I've heard about this. When I finally, well, prior to 2008, when we had to move it out of Chamberlain, I was at an open house. Ted Cox and I think it was probably Todd Hitch and I wrangled it down the steps of Chamberlain. The sonotube and the this many layers of particle board that formed the mirror cells at the bottom was way north of 200 pounds. It took all 3 of us. It was impossible to point. And and this was a couple of years later when we took it out of Chamberlain, I took it home. Spider webs were that thick in the bottom of it. We did look through it that one night, and Ted recalls it being good optic set. I've not personally tested it. I have the equipment at home. I never have tested it because I believed what the old-timers here told me. I call it the 444. It's 17.5 millimeters, 17.5 inches on the OD, but there's a little bevel around the outside, so the actual active area is 444 millimeters. When I'm doing optics, I like to think in millimeters. So all of the design work here is my own, based on what I read in Kirby and Barry, their Dobsonian book, and Tom Clark, his modern Dobsonian book, which is no longer in print. Concepts are all the same. Dobsonians have come a long way since John Dobson. Current modern Dobsonian style telescopes are what they call the ultralight types. They are all strut with a tiny little bit of stuff and what looks like a rocking chair down at the bottom. I don't trust anything that light and that small, that flimsy looking, because I like to have something that is very stiff. If you're looking at high powers, you need to be able to push a scope like this a very tiny amount to get your object centered. You don't want it sticking. You don't want to push it and have it come right back. You want a very rigid truss setup. So one of the design goals was rigid, lightweight, minimized vibration design. I think I've achieved it. We haven't seen first light. There is a vibration mode, I notice. Everyone listen. You hear that? Bong. It damps out pretty fast, especially if you have it parked on a carpet. We used PLOP software. PLOP is an acronym, stands for Plate Optimizer. What PLOP does is it uses finite element analysis to look at the worst case distortion of a mirror due to its underlying mirror cell. It knows nothing about edge supports, but it will tell you, you postulate a set of support points, and it will tell you what the deformation of the mirror is. And I'll show a couple of things later on. A second or another design goal was ease of collimation. I've worked with a number of large-sized Dobsonians. One of my first ones was the first Star Stair that I went to. A guy brought in a brand new scope. He made the mirror himself, he made the scope himself. He got me underneath and he said, turn that screw. So I turned that screw. Other way. And then 30 minutes later, we sort of had it collimated. And I thought at that time, there's got to be a better way. My first telescope I built in about 2000 to 2002, something like that, at the same time I joined DAS. And at that time, I thought, it'd be really nice to collimate a telescope standing up. So this scope, it'll be a little higher off the ground when it's got the rocker box under it. But there are two holes right here and right here. There aren't now. These go down to a lifting mechanism that supports the mirror cell. So you can sit here. Where's the focuser? Put a laser collimator in here, pointed at your eye so that you can see where the return spot is. Once you set it up initially, there's actually 3 adjustable support points in the cell. They have altogether about a 1/4 inch of travel. That's a lot of degrees in terms of mirror pointing. It also allows you to compensate if we didn't get the exact focal length of the mirror. There are some other compensation points built into this too. At any rate, you should be able to stand here like this. I was able to do it on my other telescope. Watch the knob here. If you turn these the same direction, then the mirror is going to be tilting this way or this way. If you turn them opposite directions, it's going to go this way. So you have an orthogonal adjusting thing, and you don't have to get your pants dirty. That, for me, was an important point. Most people that have used Dobsonians just get used to collimating or don't collimate at all. Pardon? They're quarter 20. They're quarter 20. But spread over that distance, you've got reasonably fine control. One turn will move you a long way. Yeah. If anything, they're too coarse. But when you're working with aluminum and stainless steel, you don't want really fine threads. It's too hard to hold the tolerances to make those threads smooth. So, for lateral mirror support, remember I said PLOP does not know anything about the lateral support. That's when you tilt the telescope, the mirror wants to slide this way, so your lateral support has got to go around the edges. What's very important there is that the support be through the center of gravity of the mirror. If it's not, if you have your support points high or low, and a lot of people that use slings have trouble positioning the support correctly, the mirror will actually take on a potato chip deformation. And you can see it in the star test. If you're holding it at the top of the mirror or at the bottom of the mirror, it makes the mirror deform. So your edge supports, particularly at low altitudes, have got to be right through the center of the mirror. And they cannot allow any vertical deformation forces on the mirror. And so the way to do that is with rollers and ball bearings and a support mechanism that uses rockers. Mike, what's his name? The mirror maker. Lockwood. Mike Lockwood, on his website, has got a good analysis of edge support on mirrors. This is not my idea. This is my implementation of the idea. All right. Eventually, all the field assembly hardware, all those screws you saw me put in, will be captive. They won't fall out. You don't have to worry about losing them in the dark. The secondary cage, as you saw, nests into the mirror box. It doesn't recess in there completely, so you're going to have something like a Subaru Outback, which is what I have. It fits in there very nicely. Or a pickup would do it. Eventually, we will have handles and wheels which fit into brackets on here so that we don't have to have the dolly to move it around. It'll be a little bit too heavy for people to pick up and carry around. So the truss connections, based on a triangle, the reason for having the triangle instead of just flat trusses is I've seen all sorts of folding trusses and everything else. Every one of them, if they're not sloppy when they start out, they're sloppy after a season of use because holes get wallowed out. So a truss like this with holes that wallow out goes like that. This truss is designed so that each of these is almost perfect compression or tension, and the attachment points are such that it goes right down the center line of these tubes. So these tubes themselves do not bend under load. A lot of fastening systems that I've seen have got a little dog leg at the end or something like that. When you push or pull on those, you're going to get a little bit of motion. I didn't want any motion. Sit still. This is a drawing. This was done on on the computer, and it's not a really good slide. But inside the tubing is a milled out piece like that that allows us to use a set of pop rivets. Now, pop rivets, when you set them properly, expand to fill the holes that they're put in. David used a lot of pop rivets on his telescope. It makes a good fastening thing. And I've got 4 of them on this side, 4 of them on the other side. I don't think things are going to move very much. So this was the jig that we used to assemble them. Have all kinds of pictures. This guy was an ad man once, so he's used to taking pictures of things. He wanted to document this. We have hundreds of pictures. I only have 100 to show you tonight, so. This is the output of PLOP. It gives you this really nice color thing over here. It's very, very, very pretty, especially if you go up to like 96 points of mirror support. What the blues and the reds are elevation. So the blues are the high points due to the mirror support underneath, and the reds are the low point in the center. Now, if you have a Newtonian telescope, the center of the mirror is in the shadow of the secondary. You could put a frog there and it wouldn't change your optics at all. The difference between low and high is given to you on the computer screen. There's a little chart that tells you how many nanometers high or low that it is. And it's like between there and there might be 5 nanometers. It's infinitesimally small. The other output that PLOP gives you is the exact design for the support system, along with drawings that show the dimensions. Just that drawing is not all that you need. You have to have exact dimensions, and it turns out if you vary those dimensions by more than a few millimeters, you see changes in this, and the changes can easily get big enough to destroy your figure. In mirror making, one trick I've had each one of my students do, you're grinding your mirror, you're polishing your mirror, trying to do everything right, and then you put it up on the test stand under the Foucault tester. If you put your palm of your hand on the mirror and you put it up on the Foucault tester and you null out the mirror, you will see a thermal imprint of your hand because it expands the glass. That's how sensitive glass is, and those are the precisions that you have to work to. And once you get a precise paraboloidal surface, you have to support it in such a way that you don't destroy that. It's not easy to do. This is what the mirror cell looks like. These are the rocker bars. They just go like that. Hidden under the triangle is a ball joint with greased, fairly good precision brass ball set into a spherical socket. You can just barely see them on here. There are little anti-rotation tangs here so that these things don't rotate. If you rotated, you would put your pressure points in the wrong places. So these two sit on top of this seesaw. Those two sit on top of this seesaw. The seesaws have roller bearings, very low friction, because they carry the most weight. And these are the mechanisms that raise the 3 corners of the triangle that support the whole mirror. Right up here, buried right in there, is a socket head screw. So an extension screwdriver goes up to the top of the box right here, and it just sits there waiting for you to put your Allen wrench in to do your collimation. These were fun to make, fun to design, and fun to make. It's basically a sliding thing on 2 rods. The up and down is controlled by the screw lifting the little within the window, the little holder. Now, going from here into here, there's a precision hole, another precision brass ball, a 1/2 inch stainless steel shaft in the brass ball. So as you raise it and lower it, because of the orientation here, this is an axis that goes up and down. You can also raise this higher than that one over there, and it pivots around this point so that it goes the other way. Over small distances, it's a very precise motion. You wouldn't be able to chase asteroids with it, but it works. Because the telescope is built with high accuracy, you don't have to collimate. You don't have to move the mirror very far to collimate. The secondary cell, this was another fun part. Most secondary cells are held in place, or secondary mirrors, which are elliptical, are held in place by a sheet metal thing that's got a little lip underneath it. It works well. It's sort of the standard way of doing things. If you go to Astrosystems or almost anybody else, you'll get a spider with a mirror holder that works like that. The problem in my mind is you go to a lot of trouble with the primary mirror to come up with a 3-point cell, a 6-point cell, a 9-point cell, or in this case an 18-point cell, not in this case but our primary, an 18-point cell. And you ought to do something like that with the secondary. If you hold the secondary by the edges, you're still going to get deflection in the secondary, which is just as damaging to your final image as deflection in the primary. And the trouble with the little round things with the turned under edge is you have no idea where the actual support points are. Physics tells you there's only 3 support points for a flat plane, but you have no idea where they are. Now, in general, for ATM work, people advise against gluing mirrors into things. So if you're going to glue it, you have to know what you're doing. This little funny thing that we call the froggy, these are basically round pads that are glued to the elliptical mirror cell. And these are little rods that allow the aluminum to expand differentially compared to the Pyrex secondary mirror. So over a wide temperature range, you now have a structure here that moves with the mirror but doesn't change the centering point of the mirror, so you can accommodate temperature changes without inducing stress, and we use silicone glue under these pads onto the mirror. I don't have a good picture of the way that is, but if anybody wants to look at it up here, you certainly can. This is the spider with Froggy mounted in it. This is chrome moly steel, which we sawed out by hand with my jigsaw, and eventually we brazed on the fittings onto the ends right here. This goes from here to here. This goes from here to here. Now, why doesn't it go straight in and cross right at the center? Because you put a sizable mirror in there. Spiders that go straight in like this have a torsion problem. You can put a little bit of torsion on the mirror, and if you thump it, it can go. Well, when it goes like that, your image goes back and forth like this in the mirror. If you offset the connection points, then you prevent that rotation. There's a number of spider ideas like this floating around. They aren't very popular. Somebody asked about curved vanes. Personally, I don't mind the fraction spikes. And in the second place, curved vanes do not have the rigidity that you really need to have to hold your secondary mirror in position without flexing. So I love the look of curved vanes, but functionally I don't think they work very well. This is the cage, picture we showed before. Baltic birch plywood, maple struts that are carved out on the inside to lighten it a little bit, and then lightning holes. Now, I don't think they actually save very much weight, but if your telescope is struck by lightning, maybe the lightning will go through the holes. So this is the OTA, which you see sitting in front of you. The reason for showing this is that a Newtonian telescope is conceptually the simplest kind of telescope that you can have, which makes them popular for ATMs to build, right? When you really start thinking about everything that goes into an optical system, and you want to make your OTA capable of being taken apart, put it back together repeatedly, etc., and so forth, you got to get everything right. It takes a lot of thinking and a lot of figuring a lot of figuring out where shims are going to be, a lot of thinking about deflections. So it's not for the faint of heart. It's for those that really like building things. If you don't like building things, there's lots of telescopes on the market today that work just fine. All right. I have gone through the spectrum. You may have noticed that we went blue to magenta. That's the end. Any questions?
Stuart, could you go back to your mirror cell and show the edge? Talk about the edge.
That one?
We can take the mirror out. If people are interested enough to take the mirror out.
Well, you can see the edge supports right here in the box. So you want to know how those work?
I was curious. I was thinking that when you were first talking about it, that when they touch would be parallel to the circumference. So here, they're just like a perpendicular to the black.
Well, you want the mirror to be able to move virtually without friction this way. So your rollers have got to be perpendicular to the edge of the mirror. Because if your mirror moves because of thermal expansion or your warping of some of the rest of the support system, whatever, the edge has got to be able to move completely freely. So you've got a little roller like that allows the edge to roll up and down. And on these guys, in here are roller bearings and stiff shafts. That's why these look so big and heavy. So that the rocker has almost no friction at all. The rollers, in turn, these are Delrin turned on a lathe with a press-fit ball bearing in them. So there's very little friction on the rollers as well. So in theory, the mirror can move up and down. It doesn't because its weight is supported by the mirror cell underneath. But the edge support's got to be completely free but not allow the mirror to move sideways.
Doesn't the edge support when you've got the two horizontal, you're supporting the edge on 4 points? That's stress concentration.
If you look on Mike Lockwood's website, he's got a long practical evaluation using star tests, etc., of what it looks like. And he finds that this kind of configuration is actually superior to a sling in most places. Well, it's a moderately thin. This is 17.5 inches, 1.5 inches thick. It's most people call it a thin mirror. Yes.
Stuart, that was your own architectural design, the OTA, like the way the plans look. You came up with that idea.
Well,
Design.
yes,
You didn't follow
except that, no, I start from scratch.
Great.
I start from scratch. I hear a lot of people say, I'd like to build a telescope. Can somebody send me some plans? Well, I never saw a plan that I liked, so. Any more questions? Yes?
One thing that I'm a bit bothered by is the focuser at the top of the cage. Aren't you going to get an enormous amount of stray light coming in?
No, because we have this thing that goes on there. This was also kind of fun. We've got felt on one side of it. We've got some semi-black stuff. This is the blackest stuff I could find. It's sold by Scope Stuff. And we've got carbon fiber in here and here. So it's a spring-loaded thing that sits right in there. Might get it to fit in there. A couple of little brass tube sockets right in there. From the focuser, if you're looking in here, at no angle can you see anything but black. It's either the inside of the tube or this up here. For those people that like looking at stars when the moon's right over there.
Stray light is usually
It's really, even Newton was baffled by this.
Yeah. Or was it sufficiently bad?
Will you eventually be able to use it for solar vision? You know, if
Well,
that's what you want to use it for?
you could. The way you would use it solar is you would cover up this and make a couple of little holes like this in the top cover. It's too big a telescope to look at the sun with. Small telescopes do just fine on the sun. It's kind of optional. I've looked at ray tracing, trying to figure out, you got light coming down here. If it hits any of these flat surfaces, it's going to go this way. However, you could have something coming in this way. The inside of the box is very black, very dark. Tom Clark, who has a 16-inch, well, he's made a lot of telescopes, but 16 24-inch telescopes, he said, in light-polluted places, or when you really have a light problem, the shroud is helpful. If you're in a dark space, the shroud is superfluous. If you stop and think about it, stray light that goes through there doesn't hurt you at all.
The inside of the trusses are going to be black. They will have the
We're going to
same
put
flocking
more of this flocking on the inside surfaces, so that stray light can't find its way back to the focal plane. But the outsides, I think we're going to paint the same color that we painted the. This is aluminum flashing. Very lightweight, very strong, very thin. Spray painted with a metallic paint. I like it. Until we got this assembly, we didn't have a way to do it reliably. It depends on the mass and center of gravity of this part. These things are very lightweight, but they add something. This weighs about 10 pounds with a good heavy eyepiece in it. So it's somewhere right around here. And the side bearings that you saw, which we have milled out, we didn't bring them tonight, they'll be mounted on this surface. They'll protrude up here a little bit. The center can be located. CG, pardon? By drilling new holes. Every amateur-built telescope that I've ever seen has more than one set of holes in it. Yes. Okay. If you're new to the hobby, unless you are a good machinist, unless you really like to build things, in my opinion, there's no point in building your own telescope. If you, like me, are obsessed with building, then it makes sense. But there's a lot of good telescopes on the market now. Celestron, Orion, Jumel, GSO, they all make pretty good optics. And if you just started out, for $500 you can get a nice 8 or 10 inch telescope, and that would be the place to start. Uh-huh. Well, if you were to buy a new optics set like this, you'd be looking at $2,500 or more.
That'd just be for the mirrors.
For the primary and secondary mirrors.
We're going to buy the whole scope from Obsession or Star Watcher or wherever else, north of $10,000. And that's not eyepiece.
Yes.
Kind of signals that I do love building things. Hour-wise, how much time?
Please retire.
Figure, with all of the thinking, because there was a gestation period, from the time that the conception occurred until there was an actual fetus, and then until birth. Do you count that time or not? Well, I've been thinking about telescopes and learning about telescope design for more than 10 years. This one in particular grew out of ideas that I had when I was teaching mirror making back in about 2006. I have other ideas, other telescopes that I want to build. So in terms of time, Digby and I have spent not every week, but frequently a couple of days a week working in my shop. Now, he's very handy in the shop. He doesn't tell a lot of people this, but I'll tell you that he's an old motorcycle racer. He knows which end of a file does the rasping, you know. So he's been very helpful. And especially he's been helpful because as I talked about this project over the years that I kept reminding people, I got this mirror set at home, you know, belongs to DAS. If I'd kept quiet, I could have walked off with it. But the club as a whole, we had a dark side. Most members here, especially the ones with gray hair, have all the telescopes they want. We have started to attract a younger set of people and new members into the club. So Digby's going to talk about this next. I'm finished with my talk. Yeah.
There's books on telescope making, if you don't want to design your own, there are some very good books out there.
Kirby and Barry, whose books, I forget the title of that, but what's the publisher, David? Wilman Bell. Wilman Bell published it. Oh, yeah, hold that up, George. That's my copy. David Kirby is the guy that started Obsession Telescopes. He and Richard Barry did a lot of, well, they built a lot of telescopes, but they also did a lot of really empirical research, finding the best bearing materials, the best structures. I mean, all kinds of things like they really did a good thing by publishing that book. Yeah.
Just as this is the question, as a comment that I discovered a long time ago, homemade telescopes are never finished.
Yes.
There's your answer. How long are you going to live? That's how long it takes to make your perfect telescope.
Something for you to consider. So if you really want to build your own telescope, you buy a kit. Buy a mirror, buy a secondary. There are very good kits out there in the market that do a great deal of the grunt work that we did here, where you could get going a lot quicker.
Yeah. Just, my design imagination goes kind of nuts. So I get myself in tight places all the time. Yeah, Dave.
You contemplated
Tracking it? You want to look at more than Polaris? A Dobsonian can be built as an Altaz tracking machine. There are a couple of systems on the market that will let you motorize it, and it can track, even though it's Altaz, it'll track the sky. We didn't want to go there. We wanted a conventional Dobsonian because the idea is new members who don't yet have their big telescope but want to use the dark side, and they've maybe taken our small loaner telescopes out for a number of times and they're wanting to look through something bigger. This can play a role. That's our thinking.
David, also to your point.
We can also put it on an equatorial.
To your point, Ted Cox has got the table that he made. It just needs a stepper motor. So
And I promised him 12 years ago that I would supply a stepper motor drive for him.
That certainly could be something that's in the horizon.
It's a possibility.
You were talking about vibration.
Uh-huh.
And we thought about filling those tubes full of some kind of foam.
I've heard that recommended as a way to, it is a dampening factor in there. Yeah. These damp out fairly fast. I was just surprised the first time I hit it because I expected it to be really dead. But while this wobbles, it doesn't necessarily translate into length changes right here. Or the length changes are very small, unless you really whack it. But mostly, you're moving it gently, trying to find your target over there. So I think that the damping on this thing in a Dobsonian mount is going to be pretty nice.
On the subject of tracking, I don't know how many of you, we used to go down to SS Optica, and Tim Haynes, who is the proprietor there, built himself a little pair of binoculars, two matched Takahashi 6-inch apples on a Dobson type mount, completely computerized, completely goes to vision tracking. And we were sort of anticipating what would that cost, and none of us could count that hard.
And he doesn't know either.
Yeah, I'm probably scared to death.
One of those things you stop counting.
It was, you know, driven and wasn't a go-to and all that.
Is there a question of Lucia? Any provision for any counterweights on the bottom?
In a well-designed Dobsonian mount, you do not need counterweights.
Oh. When you go to one of those big eyepieces that weigh 5 pounds,
Well, if those are the kind of eyepieces that you can afford. No, we're going to balance this out with an eyepiece that weighs about 2 pounds.
okay.
There are various optional ways of putting sliding weights and things like we haven't really crossed that bridge. Digby has a few more words he wants to say about the use and abuse of this telescope.
Well, again, you know, this is our dream that this is a PLOP telescope. Anybody here that's interested in using this telescope, I would really appreciate that you get in touch with me. I'll stay in touch with you as we get closer to having first light and get this thing shaken down. We will put the word out, and we'll be out there at the dark sky. And we'll try to encourage people to come out and use the telescope, even if you have never used a telescope before. This is going to be a great way to learn about astronomy and learn about looking at the sky. This instrument, if it's as good as we think it is going to be an oh wow, oh my God kind of an instrument. You're going to be able to see objects of very, very faint magnitude that you're just not going to see in an 8 or a 10 or even an 11-inch or 12-inch telescope. And
So this has twice the light gathering capability as well.
what you have to remember is that power of telescopes increases as the square of the area. So it's not an area,
Square of the diameter.
square of the diameter. Right. You remember pi r square, that formula.
Preach it to the crowd.
All right. Okay.
The boy has a good
All right.
This is not a big telescope. There's an awful lot of big in this telescope. A lot of people like David and others here have been around with big aperture. It gets weary climbing the ladder. It gets hard to hoist the telescope out of the car. So this is a moderate-sized telescope. My first star stare that I went to, I spent half the night with the guy named Gary, one of his last name Springs, a 30-inch telescope. It was the most beautiful night I think I've ever been out, so I was totally scored.
So when are you starting on your 30 inch?
I'm not going to go to 30 inches because I want to put CCD cameras on, so I'm stuck at 20. 20 inch and CCD.
Oh, yes.
Well, we have a Sky Commander system that we're going to put on this.
How does this scope compare to the Alton Clark in terms of image quality? It's much lighter.
There is much less chromatic aberration.
All right. You have more words to say, Digby?
I'm good.
Okay. All right.
Anybody who wants to look at the innards, we'll show you the innards here if you want to come down.
And Sam,